Hey, I've been doing a lot of lower level debugging at work lately. Specifically, our service has been experiencing some memory starvation and just exhibiting some strange patterns around memory usage that is affecting the reliability and health of our service. I've been digging into that, and I wanted to make a video to share some of the stuff that I've learned. I think lower level debugging like this, it's a skill that I've kind of just had to learn on the job, and I wish there were better resources when I was first getting into programming to learn this kind of stuff. So I just wanted to kind of distill some of the basics and share it with everybody. So to talk first, just briefly about a brief outline of what I want to share. Just start with an intro and then briefly talk about the anatomy of the program in memory, just kind of what it looks like and what are the relevant structures for this kind of investigation. And then finally, I'll just show a brief demo in WinDbg with just kind of a dummy API that I've built that intentionally has some problematic memory patterns. So first, just a brief introduction. I think the core problem that I want to talk about is the question: what should we do when there's a problem with our service when it's running in the wild? It's pretty easy to add a breakpoint to your code and step through it when you're developing locally to understand how it's behaving. But when your code is deployed in the cloud somewhere or something, and something goes haywire, it gets more difficult to understand what's happening. So typically, we will use logging to understand exactly how the program is behaving. But there are times where logs aren't good enough. For example, your code you might be maintaining legacy code that doesn't have good logging. There are also just a suite of problems that are very difficult to diagnose strictly through logging alone. Some examples would be like memory starvation, CPU starvation, thread starvation, deadlocks, that kind of thing. Logs are typically, you might have logs that log, the thread count and stuff like that, but it's probably not common. And these problems can generally, manifest in a lot of very strange ways that it's not always obvious what the root cause of the problem is. So typically, with these kinds of things, you're going to be using metrics, not logs. For example, you might have a metric that tracks the size of the heap in your application, and then you could track it over time and alert when it passed a certain threshold. That would be a pretty common thing. Same with thread count and CPU. But once you know that memory starvation is a problem, what do you do from there? It can be difficult to actually find the root cause of that, and that's what I want to talk about today. The skills that I'll be talking about here are mostly applicable to these other problems as well. The things specifically that you're going to be looking for will be different, but the tools will be similar and the thought process will be similar. So mostly just going to talk about memory starvation. So next, let's just talk briefly about the anatomy of the program in memory. So there is a really good, let me see if I can pull it up. I'll share this link so you can look through it, but this is an article that I've kind of been going back to many times over the years. And this guy has done a great job of, dissecting the anatomy of what your program looks like in memory once it runs. There's a lot of different structures here in memory that your program uses to function. The important ones for what we're talking about today would be the stack and the heap. I'm sure most of you are familiar with what these structures are. The heap specifically is the most interesting one for us when we're talking about memory starvation. So in a Windows application, anytime you instantiate memory dynamically, like let's say you use the new keyword to instantiate a new object, that's actually going on the heap. It's a region of memory that is allocated by the .NET runtime, and the .NET runtime is responsible for creating objects and putting them on the heap, maintaining references, all that good stuff. The garbage collector is what keeps track of them and cleans them up when nothing references them anymore. So typically, if you're seeing memory problems with your application, the heap is generally a good place to start looking. Sorry, let me close Steam. Oh man, come on Steam. Okay, sorry about that. So yeah, the heap is generally where you want to start. So basically, long story short, what I'm going to be showing today is how to get a process dump and how to open it in WinDbg and some basic commands to kind of look at the heap. And once you've identified some clues in the process dump, how to trace that back to your code and find the root cause of the problem. So just to get started, I'll kind of briefly show the mock code that I've written here for demonstration purposes. So it's basically just a .NET 8 web API. It's a game review API, so you could create and retrieve game reviews. For example, you could do list game reviews. It's going to return all of them. You can do get by ID. It's going to get them back. It's basically just an API that's hooked up to Cosmos DB in Azure for the database, and then Application Insights for logging and metrics. Application Insights is just what I'm familiar with. At work, we have a proprietary logging and metrics and monitoring system, but I can't really use that from my personal machine. So I've also heard good things about Grafana, which I think you can use like open telemetry and all that good stuff for. I didn't have time to figure out how all that stuff worked. So App Insights is pretty easy to hook up. So I think, I probably wouldn't use App Insights for a production system these days, but it's pretty easy. So it's good for a demo. So basically, yeah, this API is running, and I'm emitting two metrics. First, you'll see this instrumentation attribute. This is basically just tracking. You annotate controller methods with this, and it will emit a metric, which is the status code. I'm sorry, the request duration is the metric value. So, this might be useful if you wanted to monitor how long it was taking your API to respond. It would be important to know if your API started getting slow. You'd probably want to be alerted for that. And two custom dimensions would be status code and the endpoint, which is basically just this string. It's just an identifier. So, you could set up a monitor to alert you if status code, the threshold of 500s got too high, or if the request duration got too high. And then the monitor would also have the endpoint to tell you which API endpoint was unhealthy. So this isn't necessarily relevant to the memory starvation problem, but just to kind of give you, if you're not super familiar with metrics and monitoring, just to give you a brief idea of like what kind of stuff you can do with monitoring that might be useful for an API. So that's one. The other one that's going to be more relevant to this discussion is I'm also emitting a metric for just to track the size of the heap. Basically the total bytes of all memory allocations on the heap. That is useful so you can keep track of how much memory your API is using. And I have personally experienced problems at work where the memory usage will grow unbounded until the API is restarted, or at some point you would try to request more memory from the operating system and it would fail because there's none available. So then your application would likely crash. So it's a good thing to keep track of and monitor very proactively. Now, if you do get an alert that memory usage is getting high, what do you do? So that's what we're going to talk about. First, just to briefly show you, so here's App Insights in Azure. So if we wanted to look at this, you could write a query. Just want to make sure that's the right. Yeah, that's the right metric. Okay, cool. So you can see the metric gets emitted here with just a value. This is the size in bytes. And what we can do is we can do summarize average. And then we can do a bin, which is basically going to bucket the values into different time windows. Just do 5 seconds. And then we can render it as a time chart. Oh, and actually, sorry, we should set a time filter. Do the last 5 minutes. So, or we can even probably do the last 15 minutes, because I've just had this API running for a while. So you can see here, memory usage is kind of growing over time. This is generally not a good sign. It's not a good pattern. There's probably some leaky resource or some unhealthy caching pattern or something like that would be causing this. But if let's say you get this alert. Now what do you do? I'm running the API locally here, so it's pretty easy for me to take a process dump. Now it totally depends on, what your cloud provider is and what resources you're using. Like, for example, in Azure, app services and service fabric and all that good stuff, they generally provide the ability to acquire a process dump. So it's just kind of, it's going to depend. But the general idea, is once you get the process dump, I think the rest of the stuff that we're going to talk about will apply. So what we'll do here is we'll just take a process dump of the Vesper API. So in Windows, you can just, in the task manager, it's easy to do. I think you can do this programmatically too, but we'll do it like this. Okay, so it's going to give us the location, and then let's just copy this over to dumps. It's 2 gigabytes, that's pretty big. All right, so next, let's open up WinDbg. So WinDbg, you can also open up process dumps in Visual Studio. There's other debugging tools you can do. Hey, Weasel, go on. There's other tools you can use. I'm just familiar with using WinDbg for this kind of thing. So once you're in here, you can open dump file. Okay, so once it's open, Windows applications, the executable files, they follow a very specific convention for how things are laid out in the file. At the top of the file, there's always going to be something called the process environment block. So you could run bang PEB. This just shows you some interesting metadata about the application. Like, it'll show you all the different modules that are loaded. So like, NuGet packages, other DLL references, stuff like that. You'll see there. You'll also see all the environment variables. Just interesting, worth noting there, but not super important for what we're talking about. So we know memory is high. So the first thing I would generally do is run the command dump heap stat. Dump heap is going to show us everything that's allocated on the heap. The stat is basically just going to summarize by the object type. Otherwise, it would be way too difficult to understand the output, because there's just going to be so many objects. But dump heap stat is useful. So now this is kind of where you need to think creatively. There's not, once you're in WinDbg and looking at stuff, there's not always a silver bullet solution to exactly what you want to look for. You just kind of have to use your intuition and your knowledge of the application you're working with to identify clues and patterns that might point to something unhealthy. So what I can see right off the bat in this one is almost 2 gigabytes of this byte array being consumed. So that's suspicious. Now byte array, it might be difficult if your application is very small, you could certainly go look through the code and probably find where byte arrays were being used and maybe find the problem. Now, if your application is sufficiently large enough, it's going to be very difficult to figure this out just through code analysis alone. So this is where some other commands in WinDbg can help you. We can actually look at a bunch of these. So when we click on that, it's going to show us all of the different byte arrays. The way that you can read this output is there's 3 columns. The address is the specific object. The method table is going to be the type, which is byte array in this case. And then the size is obviously the size of the byte array. So just a bunch of random ones. And then down at the bottom, you'll see there's a bunch that kind of look the same. They're the same size, which is suspicious. So if we click on that, on one of those, and actually, yes, we'll click on one of those. Sorry, I think what we actually want to do, because basically what we're trying to understand is what would be referencing this, so we can find out, where is the code that's actually allocating these and keeping a reference to them. So to do that, we can actually run the command gcroot and then give the memory address, and this is going to show us basically a reference tree of all the of where the root of this object is. And right off the bat, generally in this case, there's going to be a whole bunch of noise from just the .NET runtime, like all of their async stack and all the web host and stuff like that. So to cut through that, you generally want to be looking for namespaces in your application, in your runtime code. There might be times where there would be memory problems in .NET and stuff, but it's very unlikely, right? That code is super heavily optimized and stuff. There's probably not a problem somewhere in there. So you can see here, Vesper API, this is the API that I was working with. And we see this class performance metrics emitter. And it seems like that class has a list of this type, this junk. And then one of those specific elements of this list has a byte array. So this is a very good clue of where we should be looking. So now we're going to go look at the performance metrics emitter type. You'll see that right here. And sure enough, there is a private read-only list of junk. And you'll see this method, apply memory pressure, which is basically just a loop where every 500 milliseconds it creates a new junk object, and that junk object has a 1 megabyte size byte array. So obviously this is an extremely contrived example, like you would never write code like this, that would be stupid, but I have seen a problem that's similar where in this case there was a controller that, I'm sorry, I take that back, it was a service. So in your service layer, now this service, you'll notice, is registered as a singleton game review service, which means one instance of this class will be instantiated at the start of your application, and it will never be recycled. It'll just stay in memory, which means any private fields and properties and stuff will also stay in memory for the lifetime of the application. And the code that I found basically looked like this. Something like, boolean string. Oops. Okay, so it's a concurrent dictionary. And essentially what was happening is the developer was using this as a cache, basically, where imagine on the get by ID, it was doing something like if cache contains key ID, it would just return the element from the cache. This obviously would have to be the right type and all that stuff. But you get the idea, right? If it was in the cache, they would return the one in the cache. Otherwise, they would retrieve it from the database, add it to the cache, and then return it. Now, consider the problem here is like this is just a concurrent dictionary. That basically means the cache entries would never be evicted. This cache will just continue to grow over time forever, and you'll eventually have to restart the service to fix that. So generally, for things like caching, you'd want to use like, if you wanted an in-memory cache, there are constructs built into .NET that provide caching with eviction duration and stuff like that. Or you'd want to use a distributed cache like Redis or something like that. So, and now keep in mind, this was, there's the service I was working with was massive, and there's no way we could have found this problem just by like looking through all the code. It's like looking for a needle in the haystack. So in cases like that, having a process dump that you can actually analyze the heap is extremely helpful to find problems like this. Cool. So I think that's probably it. Yeah, let me know if this is interesting. Maybe I'll go into some other examples like CPU starvation, thread starvation, that kind of stuff. Or I'm in general very interested in monitoring and alerting, and I've also thought a lot about things like synthetics testing and just proactively testing code when it's deployed to make sure that it stays healthy. So cool. Thanks. Bye.